We are going to be taking a look at existence and uniqueness today. It's something that's kind of been lurking in the background this entire first 4 weeks of class, dealing with solutions to differential equations. But we're going to spell out a couple of the important things here and kind of go back over some material that you've seen a little bit of previously, but we haven't said as much about, and that's the idea of intervals of existence for solutions to differential equations. So the material that we're talking about here is mainly going to come out of section 2.4 and 2.8. Now, normally I would be a big fan of you reading the textbook over any of the material that we do. I will tell you, though, that reading section 2.8 is not going to look very close to what we're doing today. Section 2.8 introduces the existence uniqueness theorem, but section 2.8 spends almost the entire section devoted to proving it, which is something that honestly I didn't do till graduate school. So section 2.8, I don't particularly like the way they've handled. What I'm going to do is try to give you all the useful applications of the theorem that's introduced in section 2.8. So I'm going to focus on the applications rather than the proof. If you would like to read the proof of the existence uniqueness theorem, you can read through section 2.8 for that, although it will not be useful for us in this course. Just highlight some things that are due. I believe today you have homework. WebAssign homework for autonomous equations is due today. So things like comparing phase lines and phase plane and finding equilibrium points and looking at what that means, those sorts of things for that homework. Also, if you're going to do corrections on MapleLab 1, please try to have those in today. And then I'm assuming you've either started looking at MapleLab 2 or you're going to get to it this weekend, but MapleLab 2 is due Monday night. I will reserve a little bit of time in class during lab for questions Monday night over MapleLab 2, but it is due that night. So you are probably going to need to have some work done. So basically what I'm saying is if you can have some MapleLab 2 work done, I'll try to reserve around half of class Monday night for answering some MapleLab 2 questions, and then it'll be due later that night for you to finish it up. All right, so let's talk about existence and uniqueness theorem. We'll start with the context of today's lecture, which is trying to get our heads wrapped around what kinds of problems can we and can't we solve in a differential equations course. So what is called a well-posed problem. This is something that is incredibly important for partial differential equations, less so in here, but there are some things in this course that touch on this. So the term, the mathematical term well-posed problem actually comes from a French mathematician, Jacques Hadamard. If you've heard of a Hadamard equation before or a Hadamard integral, that is where this comes from. All right, let me see if I can upload the blank copy real quick. I thought I had it on there, but maybe not. Yeah, you're right. I don't have it on there. Okay, let me do that real quick. All right, it should be linked in the files and on the existence uniqueness page. Thanks for letting me know. Okay, so there are three parts to a well-posed problem. A well-posed problem has to have a solution. It doesn't make sense to have a problem that you can't solve. So there must be a solution to the model. There must be only one solution to the model, which means that if you supply me with initial conditions, I better be able to only get one answer out of that. Otherwise, which answer do I go with? Which answer actually reflects what the model is going to be doing? So existence and uniqueness are the two pillars of any problem we look at in this course. We want solutions to exist and we want them to be unique when we supply initial data. The third one is a tricky one. It's called continuous dependence. Continuous dependence means that if you have two solutions which start close to one another, so if their initial data is close, then those solutions remain close for a small period of time. They can diverge over time, but at least initially they remain close together. The reason this is important is think about if we were developing a model for doing a chemical reaction, and the model predicted it would be an endothermic reaction if you had a certain amount of starting material, and it would be an exothermic reaction if you had a different amount of starting material. But what if the difference between the two amounts of starting material were so close that you couldn't reliably measure which one was which? Well, then that's a terrible model because you can't tell me how much to start with, and it can go in two wildly different directions depending on how much you started with. So that's something that's known as continuous dependence, is that initial data which starts close together should progress relatively close together, okay? That'll become a much bigger deal in partial differential equations than it is here. I will say, if you want to know a little bit more about that topic, we're going to look at existence and uniqueness solely in this lecture. Continuous dependence, I have a video on Canvas for that, if you want to dive further into it. It's not something that I'm going to talk about in class proper, but if you want to look at a video of it, you're more than welcome to. Continuous dependence is not something that'll show up on any assignment this semester, on any exam this semester, but it is one of the three main things we need for a problem to be well posed. I could ask you on an exam for what are the three things you need for a problem to be well posed, but I'm not going to ask anything having to do with continuous dependence in specific. All right, so on to the theorem. So this is the statement of the existence uniqueness theorem. I don't really expect you to have this full thing memorized, but I do want you to know the two hypotheses, okay? So the hypothesis for existence is the following. If you have a function that's continuous in a rectangle, so this is the hypothesis for existence. So what you need is continuity, right? So our differential equation that we're looking at is y prime equal f of t comma y. So you have a first order differential equation. You've taken everything except the derivative and you've placed it on the right-hand side. So the function on the right-hand side should be continuous in some rectangle around the initial point. If you have a rectangle on which the right-hand side of the function is continuous, then a solution will exist. That is a hypothesis for existence. If, in addition, you can take the partial derivative with respect to y and that be continuous, then that is the hypothesis for uniqueness. Meaning if the partial derivative with respect to y is continuous around the initial point, then you would expect there to be only one solution to the initial value problem. That's called uniqueness. Now, this theorem, like any other theorem in mathematics, suffers from a lot of notation being used, right? There's just a ton of notation here that's sort of obscuring what actually is going on here. So let me draw a picture to explain what the theorem is saying. So if you have t versus y, so I'm thinking of your solution now. Your solution has to begin somewhere, okay? So I'm going to start my solution at t naught, y naught. That is my initial condition, okay? And what the theorem says is there better be some rectangle in this solution plane where I can at least get started, okay? So I've got some interval here, a to b. I've got some interval here, say C to D, and the rectangle that's created is this rectangle here. Now, that rectangle could be very, very small. It could be very, very big. I don't care. But there's some rectangle around my initial point. And the initial point doesn't have to be in the center of the rectangle, right? The initial point could be closer to the sides. It doesn't matter where the initial point actually is, so long as it lies inside of some rectangle. So the hypothesis for existence is whatever this function is, it doesn't have any bad points in the interior of this rectangle. The partial derivative of it with respect to y, in other words, you take the derivative with respect to y, not t, of the right-hand side of the equation, needs to also not have any bad points inside this rectangle. If both of those conditions are satisfied, here's what we can say. We can say that starting out at the initial point, you can extend the solution, whatever the solution is. So I'm following the slope field here, but you can extend the solution at least epsilon beyond your starting point. And you can extend it backwards at least epsilon beyond your starting point. So this is called an interval of extendability. And so long as everything inside this rectangle is fine, you can probably extend it all the way out to the boundary of the rectangle. Where you run into problems are at any points, t comma y, where you lose continuity. So bad points, we call them singularities. Any points where you lose continuity threaten the existence of solutions and the uniqueness of solutions. That's what this theorem says. Now, there's really not much more of it for me to say than that. The hypothesis for existence is continuity. The hypothesis for uniqueness is continuity, but of the partial derivative. That's what the theorem says. You can always get started locally. You can always start your solution so long as there's no bad points. So the only way that you can't start a solution is what? This theorem says you can't get started if what is true. Right? What would it take for there to be no rectangle available? What must be true if that's the case? For us to lose existence and not be able to form a rectangle around our initial point, what must be true about that initial point? Okay, when you say it doesn't exist, the initial point exists, but the function on the right-hand side is discontinuous at that point, right? You're starting off on a bad point, right? That's the only way in this class that we will fail to have existence, is if we choose to begin our solution at a point where the right-hand side of the differential equation is discontinuous to begin with. We shouldn't expect good things to happen there, okay? And we're going to look at a couple of examples of this today, just to make sure that we understand what I mean by that. But this feeds directly into some of the error messages that you're going to get this semester in Maple. When it tells you cannot extend the solution further right of whatever because the singularity is present, that means you're trying to extend the differential equation outside this rectangle where everything is nice, right? That's what Maple's telling you, okay? So let's look at some examples of this. I want you to also understand that this theorem guarantees things. It doesn't disallow things, right? So you can have a lack of continuity and still have a solution, right? You're just not guaranteed to have one, okay? So this theorem deals in guarantees, not disallowing things. Okay. So let's look at this example. And just to see how well you picked up on the theorem and what I was saying, there's a question in learning catalytics that goes along with this. I just want to see how much you picked up from our discussion here. So I don't necessarily expect you to get everything right here. But if this were our differential equation and we can start anywhere, where are the good places and bad places to start? So I want you to look at A through E. Some of them are true, some of them are not. I want you to tell me which of these statements are true. See how much we learned from that little discussion. You're just essentially looking for bad points, right? So when you think about each of these, A through E, just think, if I start out at that point, is there something bad that happens at that point? That's what you have to think about. All right, I'll give us about another minute, then we'll discuss it. All right, everybody that's on Learning Catalytics has responded, so I'll go ahead and show those results. A and B, 3/4 of you pointed those out. E was the one that we were struggling a little bit on. We'll talk about each one of these together. So overwhelmingly, the mistake that students make when they assess existence uniqueness is they don't have the equation in proper form. The existence uniqueness theorem, going back to our notes here, you must have everything on the right-hand side of the equation. So the function that you're evaluating for continuity is the function where you just have y prime on the left and everything else on the right. So looking at this particular problem, this would be, the proper way to consider this would be y prime equals divide by x would be y minus 1 over x, which is 1 over x times y minus 1 over x. So this is your function f of x, y. So I'll rewrite that here. So f of x, y, 1 over x times y minus 1 over x. Okay, so first thing to consider is existence. What is the hypothesis for existence? Well, it's continuity, right? So are there any points where this function is discontinuous in the plane? Do we have any bad points? X equal to 0. So x equal to 0, y can be anything. Actually, let me do it using A and B. So we're not guaranteed existence if A is equal to 0, right? That's the point where we fail to have continuity here. So that's what the existence uniqueness theorem tells me. A equal to 0 is bad. What's interesting, because this is another way to write this, what's really interesting here is what if we're at A equal to 0, but y is equal to 1? So A equal to 0, B equal to 1. Right? That's more interesting, because if A is 0, that means my x value is 0. And if B is 1, that means my y value is 1. I get 0 over 0 there, right? Which is not undefined, it's actually indeterminate. Okay, that's slightly different there. The existence uniqueness theorem doesn't tell me anything about that. So this is sort of a mystery to me. I don't know anything, but I for sure know that we're not guaranteed to have solutions if A is 0 and B is not 1. So if A is 0 and B is not 1, we are not guaranteed any solutions. So that is B. B is true. Okay. Let's talk about E, for example, and why E is true. E is talking about my initial point being 2, 3. Is there any problem with 2, 3 as an initial point? It doesn't do anything bad to the right-hand side of the equation. So I would expect my solutions to exist there. Okay. I'm not, the only place where I'm not guaranteed existence is along the vertical axis. Okay. All right. What about uniqueness? Well, now remember, uniqueness requires the partial derivative with respect to y, right? So I've written it in this form here to make that easy to calculate. What is the derivative of this with respect to y? So treat x as a constant and take the derivative with respect to y. Yeah, 1 over x. So the partial of f with respect to y here is 1 over x, which means when x is 0 or a equal to 0, once again, we're not guaranteed uniqueness there. So the only bad point here really is we want to stay away from 0. We want to stay away from x equal to 0 on this problem. And this is actually a separable differential equation, so I actually want to solve it with you real quick. That's going to give us quite a bit of insight here. And then we're going to look at the solutions in Maple and discuss a couple of the things that we find. So the solution here, since it's separable, I can write dy dx equal y minus 1 over x, which is dy y minus 1 equals 1 over x dx. This is the natural log of y minus 1 equals the natural log of x plus a constant. If I exponentiate both sides, I get rid of the natural logs. But then I have e to the c, which is a constant, so I'll write it this way. It's a times a constant, or a times absolute value. And this is where a is equal to e to the c. And if I drop the absolute values, I get plus or minus everything. So y is 1 plus or minus a times x. I know that was kind of quick, but we've done separation of variables quite a few times already. So I think at this point, you can kind of understand what I'm doing there. I don't have an initial point in mind, but I want you to look at that solution for just a second and tell me what this is geometrically. What is every solution to this problem going to look like? A straight line, but more specifically, every single line will pass through what point? Yeah, 0, 1 in particular, 0, 1. Yeah. So these are all lines with variable slope passing through a y-intercept of 1. And if you do the work in Maple, I've shown the Maple work here in the slides, took the differential equation, desolved it. We got the same solution that you and I just got together there a second ago. I put in the initial condition, y of a equal b. You can see that when you do that, the a ends up on the bottom, which is why a can't be 0. Right? So when you solve the problem, a naturally winds up on the bottom. A cannot be 0. And if you look, I tried to get Maple to plot the solution starting at 0, 1. We said 0, 1 was this really weird point where anything could happen. And if you try to ask Maple to plot a solution there, it can't do it. However, and it says it's singular at the initial point. Singular means you have a point of discontinuity, a point of not being defined there. However, if I ask it y of 1 equal to 1, right, it plots the horizontal line, which goes through 0, 1. So this tells me a couple of things. Even though Maple couldn't plot the solution, right? Maple couldn't plot a solution starting at the point 0, 1. This tells me there are solutions passing through 0, 1. In fact, all solutions pass through 0, 1. So the reason that Maple failed to give you an answer here is because we started off at a bad point, but it was a bad point where we lost uniqueness. We lost uniqueness there. We didn't lose existence. Okay, there's actually turns out to be several solutions that pass through 0, 1, right? Here's 0, 1. There are several solutions that pass through that. All of these pass through that. Any line through this point is a solution. It follows the arrows of the slope field. So there are an infinite number of solutions that pass through 0, 1. Where did we say we wouldn't get solutions? Right here. Right? No solutions guaranteed if A equaled 0. So along this line where the slopes are starting to become vertical, we should not expect solutions along that line. Now, did we get some? No, we didn't get any. There are no solutions on this line except at the 0.01. So we weren't guaranteed existence at 0, and we weren't guaranteed existence along the vertical axis, except potentially at 0,1, where it turns out we had existence, just not uniqueness. Okay. So these are the tools by which you can analyze when solutions to differential equations exist, how many solutions exist at a point. These are some of the tools that you'll be using on this Maple Lab. I think the last 2 questions on Maple Lab 2 deal with this sort of thing. Now, there are some consequences of dealing with this existence uniqueness theorem that I want to discuss. The first of which is something that I think you've picked up on this semester. We had a question on a skills quiz that was sort of related to this, but I want to go ahead and ask it again to all of you here. So there's a learning catalytics question out there for you to answer. And it is true or false: when a solution is guaranteed to exist for a given differential equation, is the solution guaranteed to exist for all time? Meaning, if I know I can get started off my initial point, am I then allowed to extend the solution minus infinity to infinity? Right? Can I extend it as far as I want, whenever I want, if a solution exists? So what do we think, true or false? I think we know the answer to this, but we'll see. All right, you have about another 20 seconds here. All right. The correct answer is that this is false. Just because a solution exists doesn't mean that solution exists for all time. The existence uniqueness theorem says nothing about the interval of existence, simply that there is a solution that exists on some interval, okay? Some interval. Let's look at an example of where this actually breaks down. So, big false. An example of where this breaks down is the following. So consider dy dt equal y cubed, starting out at y of 0 equal to 1. Okay, we should be able to solve this. The solution to this problem, I can get the solution via separation of variables. So this will be dy over y cubed equals dt. If I then integrate both sides, I will obtain, let's see, this is y to the -3. So that'll be y to the -2 over -2. So it would be y -2 over -2. equals t plus a constant. So if I multiply through by -2, I get y to the -2, or I'll say 1 over y squared, is -2t minus 2c. I then want to swap. I want to get my y up in the top. So I'm going to take the reciprocal of both sides. So y squared is 1 over this. And now I'm going to invoke my initial condition here. I know at t equal to 0, y must be 1. So if I plug in t equal to 0, so 1 squared has to be 1 over -2 times 0 minus 2c, which is 1 over -2c. So that tells me the c has to be what, -1/2? Right? In order for 1 over -2c to be equal to 1, c would need to be -1/2. So my solution here is y squared equal 1 over, I'm going to factor out the -2 here. This will be -2t plus c, but c is -1/2, so it'll be t minus 1/2. And if I solve for y directly, I would have to take the square root of both sides. Because the y value here is positive in the initial condition, it would be the positive square root that ends up getting taken. And let me just do it this way. So this would be the solution to this problem. So I want you to tell me, what is the domain of that solution? We're starting at 0. How far can I extend the solution? In other words, what is that solution's interval of existence? I mean, it clearly doesn't exist if t is 1/2, right? Because I'd be dividing by 0. And if t were, let's see, if t is bigger than 1/2, right? If t is bigger than 1/2, you see you get a negative under the root. Like say t is 1, right? So -infinity to 1/2 is what Jet says. Do y'all agree with him? Remember, we're starting at 0, right? That's our initial condition. We're starting at 0. So think of it kind of like a timeline. Starting at 0, I clearly see a bad point at 1/2, and everything beyond 1/2 is bad. Is there anything bad to the left of 0? No, those are all fine. So I can start at 0 and extend all the way up to 1/2 and all the way to -infinity. Seems good to me. So the interval of existence here is -infinity to 1/2. So the point to this example is, just because you have a solution that's guaranteed to exist, right? The existence uniqueness theorem would tell us there's no bad points here, right? You look at y cubed, there's nothing bad there. There's no discontinuities there. So the existence uniqueness theorem would tell us you get a solution at every initial point for this problem. And in particular, the initial point at 0, 1, I can extend it -1/2 or -infinity to 1/2. And I know you're sitting there thinking, well, Dr. Erke, if things beyond 1/2 are bad, what happens if I looked at, say, y of 1? Well, if you looked at y of 1, this wouldn't be your solution anymore, right? Your solution would change, which means your interval of existence would change. So every single initial point for this problem is valid. I can find a solution at every single initial point. The existence uniqueness theorem guarantees that. But what I don't really know is what the intervals of existence are for all of those. Some of them might be -infinity to infinity, but a lot of them are going to be less than that. You don't get existence everywhere. You get existence somewhere. That's what the theorem tells you. Okay, let's go on to one more and let's see if y'all have really picked up on this without solving this problem. So I'm not going to solve for the answer, okay? I want to look at this differential equation. We're starting out at the point 1, -3. There are several options in learning catalytics for this. I want you to tell me which of them is an interval in which I can solve this problem. Now, I might be able to go outside that interval, but which of these is an interval for this problem? All right, I think I can give you about another minute and then we'll need to talk about it. So don't try to solve it. The solution, it's a linear equation, so you could solve it with integrating factors, but the point here is not to solve it. Okay. So the results are, most of you think C is correct, and it is. Not surprised by B, though. B makes some sense here as well, but C is the correct answer. Let's take a look at it. If you were having trouble getting started on this problem, most of the time it's the very first step, which is I should set up the ODE in y prime equal f of ty form first. Right, that should always be my first step. So if I do that, let's see, you've got 4 minus t squared y prime plus 2ty equal 3t squared. This would be y prime equals, it's 3t squared minus 2ty. And then I'm dividing the leading coefficient here, 4 minus t squared over. So this is the correct form to be thinking about this problem in. And when it's in this form, f of t comma y is this function on the right-hand side. So for the purposes of applying the theorem, that's the function I'm thinking about. So I know we're starting at the point t equal to 1, y equal to -3. So can I get started? Well, yeah, if I plug in t equal to 1, y equal to -3, I get a number, right? So if at my initial point, this gives me a number. And remember, in a differential equation, the number that it gives you is a slope. So this gives me a direction to head in, right? So I can get started, right? I can get started at the point 1, -3, no problem. Where do I run into issues? Well, if you look at the denominator, 4 minus t squared, where it's 0, that's 2 minus t, 2 plus t is equal to 0. So at t equal to plus or minus 2, there are discontinuities. So the existence uniqueness theorem tells me you're going to run into problems once you get to plus or minus 2. So I'm starting at 1, and I'm guaranteed to be able to solve the problem on -2 to 2. So remember, it's kind of a timeline thing. I'm starting at t equal to 1. I can go up to t equal to 2 and over to t equal to -2 before I run into problems. So there are problems here. But I can start at t equal to 1 and I can extend up until a problem and I'm good. So interval of existence, I'll say, is at least, it could be longer, but it's at least -2 to 2. Now, I want to say a quick thing here that you may be puzzled by. Let's see if I can fit both these examples on the same screen. All right, the previous problem had no signs of issue, right? Like there are no points here that are bad. So why can't I just start at 0 and extend -infinity to infinity? Well, it's because this equation is nonlinear. And for a nonlinear equation, you cannot tell the interval of existence just by looking at it. You have to calculate a solution to find its interval of existence. But this equation is linear. This is a linear differential equation. In fact, if I write it in linear form, it's y prime equals -2t over 4 minus t squared y plus 3t squared over 4 minus t squared. This is a linear equation. It's of the form y prime equal a of t y plus b of t. That's a linear differential equation. And for linear differential equations, all you have to do is determine a of t and b of t. Where do a of t and b of t have discontinuities? And if you can determine that, then you automatically know the interval of existence. You know that things are not going to go bad for this equation so long as you don't cross any values where a of t and b of t are bad. But that does not apply to nonlinear equations, like you saw in the previous example. We ended up having a bad point at t equal to 1/2, even there was no reason to suspect t equal to 1/2 being bad based on the equation itself. So just some things to think about this semester as we go through solving more problems. Always be thinking about two things. Can a solution exist? And if a solution does exist, how far can I extend it before things go wrong? Okay, that's two questions we're going to be asking the whole semester. All right, y'all have a good weekend. I will see you back on Monday face-to-face, and we'll have Maple Lab face-to-face Monday night. If you have questions over the weekend, feel free to email me and I'll get back to you. Thanks, everybody. Yeah, Josiah, if the numerator equals 0, if you're dividing by 0, that means that that's a point of discontinuity. So it's what we called an infinite discontinuity back in calculus 1. So long as the numerator is not also 0, which would be an indeterminate form if it's 0 over 0. But typically you're looking for places where you would divide by 0. That's where we find most of these. So values of t or values of y that cause you to divide by 0. No problem. Have a good weekend.